Nina, and welcome everyone to today's webinar, Innovations in Pumped Air Sampling. My name is Ed Rutkowski. I'm Editor-in-Chief of The Synergist, a magazine of the American Industrial Hygiene Association, and I'd like to thank all of our listeners for attending today's event, and especially MilliporeSigma for sponsoring this webinar. MilliporeSigma researches, manufactures, and supplies chromatography columns and related tools for environmental, government, food and beverage, pharmaceutical, biotechnology, medical, and chemical laboratories. They specialize in 4 main product areas: gas chromatography packings, columns, and accessories, liquid chromatography packings, columns, and accessories, sample preparation products, and chemical reference standards and reagents. Our presenter today is Gary Oishi, an R&D chemist in the Environmental Air Monitoring Group at the Sapelco division of MilliporeSigma, where he helps develop new products and testing methodologies in air monitoring. Gary previously spent more than 20 years in analytical chemistry involved with the identification of micro and macro contaminations in failure analysis, deformulation, forensic, and industrial hygiene sample testing. Now I'll turn the controls over to Gary.
Good morning, everyone, or it may not be morning for everyone, but let's see if I can share my screen with you. Share my screen. All right. Hopefully everyone could see my title slide. I want to take this time to actually, again, welcome everyone and thank you for taking the time out of your busy schedule to listen to me talk about innovations in pumped air sampling. Hopefully, this will be a kind of a collective learning experience for both of us. So let's get on with my presentation. Here are points that I'm going to go over in telling of this story. As you can see, we need a little bit of history or background to make sense of our direction and why these innovations. We're going to look at the kind of like the big picture, what we need, how we go about collecting an air sample, how does pulsation impact air sampling, current pump designs, and our innovations or progress in design. So starting out with the big picture. As industrial hygienists or EH&S personnel, I'm sure your goal in air sampling, whether it's personal monitoring or area sampling, is determined if there is a possible exposure so that appropriate controls can be put in place. Chemical exposure is dictated by the concentration of the suspected chemical, with regulations then specifying the limits of said exposure. So what do we need? Well, we're always looking for, and we need, the ultimate looking for that answer is concentration. That is the main driver of why we're out there doing any sort of monitoring. So pretty simple, concentration, which can be calculated by determining the mass of the suspect chemical per volume of air that the chemical was collected in. Determining the mass of the chemical is accomplished using an analytical laboratory technique. Now, over the years, these analytical techniques have technologically progressed with the advances in instrumentation. I mean, everybody, every year or every couple years in the labs are always spending more money on better equipment. Well, and we can see examples of the progression since if you, I mean, it kind of dates myself, but I've been around for quite, I'm old enough where I've seen a lot of the methodologies move from basic wet chemical techniques, so colorimetric analysis, or looking at precipitations or basically gravimetric weighings. But these have progressed along the lines of, have gone to like using UV spectroscopy, and then now even with instrumentation, and then now even at this point, instrumentation that's hyphenated, so we have LCMS or GCMS. Now this is great, having the ability and pushing the sensitivity and accuracy in determining part of what is needed in our calculation, so that massive pollutant. But what have we done over the same years in improving the other half of the information we need? The denominator, volume of air. That's critical, so we'll look at it. So let's look a little more closely at determining the volume of air. This requires 2 pieces of information, length of time, and flow rate. Time is easy enough to determine in this day and age, and measuring, but flow rate is where the challenge exists. To understand this flow rate challenge, let's look at what it affects and how. So how do we currently go about our daily business? This slide kind of shows you a basic workflow of 3 components that we deal with. We have a pump which creates our flow rate, pulls our air sample. We have a sampling media, which you're collecting your pollutant on, and some type of calibration device to accurately determine what that true sampling flow rate is. So this is kind of like pre-sampling on the top line. The middle line in pink would be how we actually collect our sample, and the bottom line, our post-acquisition. We hook our calibration device and recalibrate to measure and kind of confirm what our flow rate is. Next, these things, we currently use, or this whole process, we have flow rate. So flow rate, must be important because we're always calibrating for it. So with that said, let's kind of examine what flow rate is really all about. So in our active sampling world, what air needs to be moved through our sampling media. Most commonly, and for this presentation, we'll only be kind of talking about sampling pumps. Essentially, what is required is the ability to apply a negative head pressure on the outlet side of the sampler. This is where sampling pump comes into play. Technologically, pumps have progressed some. However, for the most part, personal and ambient air sampling pumps types create the airflow using the principle of positive displacement. This means they operate by moving a volume of air by positively displacing it with another volume of air repeatedly in hopes to create a constant flow rate. On the surface, a constant flow rate does help and provide confidence in the volume data needed for our exposure calculation. However, by design and the mechanics of moving air, today's sampling pumps have a flow profile with the characteristic of pulsation wave, as hopefully everybody can see the animation going on. So the generated wave can have a basic sine form waveform, and it would be an ideal kind of like an ideal situation, or what would be an ideal waveform. You see there's a maximum point, midpoint, and a minimum point. Remember that the total volume of air sampled is a calculation of flow rate multiplied by the total sampling time. So what do we use for flow rate in our calculation? Well, the problem often with this calculation is that the total volume of air is a measurement based on an average midpoint value in this ideal waveform, and not a true and accurate integrated measurement, which this would involve integration of the exact waveform function in a dynamic environment. Hence, the need why we use a calibration device. Many pumps today employ some sort of mechanism that operates to maintain constant flow as back pressure increases. When a pump detects the change, it compensates by working harder to maintain the set flow rate. According to ISO 13137, this would be within plus or minus 5% of the set flow rate. So right away we can see that there's some leeway in what your flow rate is going to be during sampling, hopefully. Having constant flow capability to lessen the effect of changing back pressure is essential, since a working pump is calibrated only pre and post sampling. Nevertheless, if the flow rate of the air sampling pump is not accurately controlled, if there are large pulsation waves, or if the pulsation waveform is non-ideal, the collected volume of air could be highly inaccurate, which could give an under or overestimation of the final concentration value of your air sample. And here's talk about pulsation. Here's the ISO 13137. They define pulsation, pump pulsation, as a percent. Mathematically, it's the percent ratio of the area between the pulsation wave and the mean flow, volume flow for a given time period. So for those of you who enjoy math, that's something that's kind of fun and interesting, but easily this is can be programmed into a Excel spreadsheet, and that calculation can be performed. So that kind of will allude later to in a bit. But ISO also has a specification that pumps should not exceed a 10% value for pulsation for the flow rate, and this is under certain. They have certain set specified conditions. I would refer everybody to take a look at the ISO method and seeing how they determine this as far as the conditions go. But we'll proceed from now. So here's a chart showing, I know it's a little busy, but it shows kind of like the relationship of the effect of percent pulsation on flow rate. So this is based on an ideal wave pulsation. As you can see, the maximum and minimum flow rate shown in the beige fields, hopefully that's beige for everyone, it is for me, for your set flow rate shown in the yellow fields. And they could be quite different as the pulsation value increases. So observing these pulsations would not be evident with the use of some calibration devices. So you would have no idea that these pulsations really truly exist. And as you can see, for example, if you look at the target flow rate of 1 liter per minute, so in the left-hand column in yellow, if you look across all the way over to a, say, if you look at the maximum plus or minus a 25% pulsation, what you set the flow rate to at 1 liter per minute, that pulsation could be anywhere from 1.25 liters to down to 750 mils. So you can see there's quite a bit of swing. So what do we do if you don't have an ideal, or if there is not an ideal waveform for the pump that you have? In this example, flow rate, and depending on how flow rate is calculated, you can see that there's two different flow rates. There's actually an amplitude flow rate, or mean, what would be used as a mean, or the wave function mean, and so that's already a 5% difference in that value. So are we giving away 5% in accuracy right off the bat? To further look into how pulsation affects air sampling, we took a look at a few common air sampling pumps out on the market. And here's kind of the comparison was done over 4 different flow rates from 200 mils per liter, 200 mils per minute to 2 liters per minute. And as you see, pumps don't behave or operate in the same way. Some pumps, depending on the sampling or the intended sampling range, have very different capabilities. So some have, for low flow, require low flow adapters. Some pumps, when you start using 2 devices, or you're sampling multiple sampling media on one port, you're essentially giving up the ability to record and log the true volume and flow rate. And then we actually have a dual sampling pump, which kind of takes care of some of these issues, but we'll talk about that in a later slide. First, here's the low flow that we used at 200 mils per minute, and this shows 4 different pumps. And these are the pulsation profiles that occurred. As you can see, 2 of the pumps have very low, appear to be very low in pulsation percentage. And these two only show these due to the fact that they require some sort of a low flow adapter. They weren't able to sample at 200 mils per minute, so a low flow adapter was used, and what that does is it actually acts as a way to dampen the pulsation by allowing only a certain amount of airflow through the sampling media from a larger base. As we increase flow rate to 500 mils per minute, we see that now only one pump is a really low number, and again, this pump had to use some sort of a low flow adapter or mechanism to be able to sample at such a low flow rate. But if you notice that the other samples, the pulsations, those are actually real pulsations for those pumps. Quite large, but what we'll do is we'll kind of see a trend as we go to a little bit higher flow rates. Now as we move on to 1 liter per minute, we'll see that now everybody, and for all these cases, nobody is using any sort of adapter or modification to being able to sample at that rate. Pulsations have come down, and this is beginning to look like, you know, more of an even kind of playing field. Now as we move to 2 liters a minute, the pulsations now are beginning to normalize, and this is probably due to the fact that at higher flow rates, there may be a case where pulsation becomes a less effect, and also maybe because there could be an increase in back pressure on the system, acting more or less in a dampening way. So how does pulsation impact air sampling? Let's kind of start by looking at the 3 classes of samplers used for particle sampling. We have a filter, cyclone, and an impactor. One area of concern exists on pulsation may have an impact, as it may have an impact on particle sampling, especially with cyclone and impactors. There have been a number of studies, which I've listed in my reference slide, that examine the effect that pulsation can play on sampling. If we look at the basic math involved with affected samplers, we see a term for speed and velocity, respectively. With this term closely reflecting the flow rate, pulsation maximum and minimum, so large variations could have a definite impact, as we have seen in the reference work. However, the researchers also cited that there was a point where no significant impact on sampling efficiencies occurred with pulsations at less than 25%. So again, the ISO standard was a specification for 10%, and this would certainly alleviate a lot of that concern about efficiency, particle sampling efficiencies. We'll move on to current pump designs. Today's pumps are based off a diaphragm pump. Pretty simple. This is a basic kind of cross-section of how a pump diaphragm would work. Diaphragm pumps contain a chamber, plunger, or a piston, and as the motor turns, the plunger piston, the diaphragm oscillates back and forth, which creates a vacuum and pressurizes the pump chamber. The pressure is released by pushing of the plunger or the piston downward through a combination of sensors and check valves, releasing the airflow. And as the airflow in the space flows out of the pump, as emptying basically, it's filling up again. But still, the way that these mechanically work, they do still create some sort of a pulsation, so a waveform is indeed evident or intrinsic to them. Some pumps have incorporated pulsation dampeners into their design as a way to aid in minimizing pulsations. Well, you know, that's always the good point, trying to achieved to be under, say, that 25% pulsation. But realistically, with today's pumps, most of them, a lot of manufacturers are trying to achieve that goal. So here is a diagram showing varied pump characteristics. It can be a resultant of manufacturing design. This is several different, as you can see, there are a lot of different waveforms. All of them don't look the same. A lot of them have very different percent pulsations. So given that, a lot of pumps, based on, these are all based in and are intrinsic into the design and the operation of the pump. Now, how we all measure flow rate, how that's all calculated by the pump, is certainly questionable, or could be, one pump is certainly not going to calculate it the same way as another one with a different waveform, or hopefully not. And that's why we use a calibration device to actually measure that flow rate pre and post sampling. Some pumps use dual pump design, and the way that this is incorporated is that by offsetting mechanics of the way these things operate, you move the pulsations in an out-of-phase manner, and actually, as you can see, that combination would be what your airflow would look like. So as the two pumps move out of phase, it lessens that pulsation, but cannot truly eliminate it, but it does considerably lower it. So what's new in pump design, or why is this an innovation as far as how pumps are designed nowadays? Well, let's go back and look at an earlier slide showing the simplified workflow. We have again, we have our three basic pieces needed for accomplishing our task. Have any of you ever asked the question, or even wondered, did anything happen to the flow rate during sampling? Currently you check it pre and post sampling, but how many times are there numbers, these numbers not the same? What do you use for sampling flow rate in that case? What happens if the two numbers that you get are significantly different? And those are all things that everyone has their own kind of criteria for setting what comes next. So now, what if you don't need to worry about those questions? Here is a new approach and innovation that is born. So what we've done, or what we've done, is incorporate a calibration device into the sampling pump. Wow, that's pretty simple. I mean, how does your workflow look now? So in this next slide, again, this would be what your workflow would look like. So you actually have your calibration device in line or incorporated with your pump. So you're sampling media at the beginning, so your flow rate gets measured. Your flow rate gets measured at the end as normal, but in the interim, when it's sampling, when that person who that sampling pump is hung onto or being sampled, or that area where, if you're doing an area sample, where it's sitting, and you walk away and have no idea what's going on with it. You obviously don't have a calibration device hooked to it, so you can't see what the flow rate is, or nowadays, some pumps do record some sort of a flow rate, but that's not a true calibrated flow rate because they have a calibration device that they measure that true flow rate with. So what we've done, and this allows you to actually record and see what exactly is happening to your flow rate over that period of time. So we made calibration. Calibration became really easy for everyone. I mean, it's incorporated into your sampling train. Remember that this calibrator, it's going to be mass flow based, and it's going to be NIST traceable. So it really trims the time you spend in setting up a sample, and after you take a sample, and what you do with the results after that. So another innovation in this is we have actually an improved patent airflow technology, is that we kind of take multiple diaphragms and then we put them out of phase in pairs. When having multiples positioned around a pump that actually spins on an axial basis lessens the torque resistance, thus making the pump not struggle when pulling a high back pressure or trying to pull and maintain a high back pressure. In this day and age of electronic technology, selectable connectivity is a feature via tablet or phone. So we have the ability to connect multiple pumps to a tablet or your phone. So actually you can monitor these things remotely. You can stop them if you want to delay and make sure that somebody has gotten to a position or in an area where they're going to be working, or if you have or want to set up, a more specified or focused sampling sample. So it allows you to start and stop, and also you can set whatever flow rate. So if you wanted to change the flow rate, say for some odd reason you wanted to set the flow rate for 500 mils a minute, but then when you just realize, oh, well, that's not for this sample, I need to change that. Well, instead of trying to call somebody back, you can actually remotely change that. Now, as a result of having a feature of having an integrated calibration built into the pump, you can actually monitor your flow rate and back pressure as it's occurring. So again, this gives you the ability to look at history, to make sure that what has occurred in the interim between your pre and your post calibration is actually, your pump is actually performing the way it should, or that you're actually seeing what the flow rate is actually doing. And here, kind of one of my favorites is having quick connect fittings. I mean, it's simple. I mean, it's not real technologically advanced or anything like that, but I'm sure everyone hates struggling and fighting with connecting tubing to their pumps. You can have tubing that's preset, or because everybody doesn't have the same size tubing, or people have drawers full of sections of tubing that are different size, and now you have to look for all these adapters. Well, if you have quick connect fittings, this becomes connecting to your sampling media much faster and easier. Also, we have the flexibility now, and technology gives us the ability when we, obviously we can charge the pump via plug into a wall socket, but we also have the ability now to charge a pump via USB. And that's kind of a great option. Opens up a lot of areas, especially if you're somewhere where you have no access to an outlet, or you don't have a couple 100-foot extension cord. You can actually hook it up to any portable battery pack that you typically, most people kind of carry around nowadays for their cell phones. So kind of to wrap this up now, remember in the beginning of my presentation that flow rate was an important piece of information we needed to get us the answer we were looking for. We have seen that flow rate is more complex in nature due to the intrinsic design of today's pumps. innovation has provided that by incorporation of a calibration device in the pump, we have simplified the flow rate component, thus giving us the ability to measure that flow rate. Not necessary to pre- and post-calibration to calibrate your sampling train with an incorporated sampling device, so it kind of saves a little bit of time. We are able to record flow rate over the sampling period, giving us confidence in if something happened to it, and adds the benefit of providing an accurate measurement of air volume sampled. Patent pump design now make sure that we minimize flow pulsation for potential particle sampling efficiency concerns. And Bluetooth, everything nowadays is Bluetooth, so why resist? And having the ability, and going along with that, having the ability to charge by not plugging in to an outlet, to actually being able to charge via USB, especially in remote locations. Here's my sample slide, or my slide that contains my references that I have. And I want to thank you for your attention, and I would like to thank our gracious webinar host and our AIHA, Ed and Regina at WebEx for putting this all together. If you have any questions, please feel free to either chat me or send me an email. Thank you.
Great. Thank you, Gary. It looks like we have a good bit of time for questions. A few have already come in. Just a reminder to our audience, if you'd like to ask a question, please type it into the chat window on the right side of your screen and send to all panelists. Let me go back to the questions that have come in previously. We have a question from Lucinette. She asks, if the pump will have its own calibration device, will it require an annual calibration from the manufacturer, as in the case of the primary calibrators available?
Yes, it would still need to be calibrated annually. As with any calibration device, currently what everyone is doing, and according to all the manufacturers, or if you look at what kind of everybody goes through, if anybody has a pump, recommendation for any pump is to have that pump sent back and calibrated. Also, that calibration device requires every year to be calibrated. So essentially what you're doing is you're calibrating two devices, but you only need one device to do a calibration. Hopefully that answers that question.
Okay. Thanks, Gary. There's a question from Donna. Can pumps be operated manually and data downloaded later?
Yes. There is memory storage in each pump. It creates a log file in each pump. What does occur, if you run it and it was designed, and hopefully the way when the design was done was that pumps can operate solely as a pump. They can operate in a Bluetooth or connected fashion, and also log files get created in both situations, so you don't necessarily need to plug the pump to download it back to a computer in order to pull a file if you're using it in a connected fashion. That gets downloaded or actually added to your tablet or remote device. But in order to answer your question, yes, you can download log files and see the information at a later point.
Okay. There's a question from Tambra. If sampling is done for OSHA compliance, is there any problem with acceptance by OSHA?
OSHA, I'm not quite positive if OSHA truly has an accepted criteria for some pumps. I know if you look at, or the pump will meet ISO specifications, so that would certainly be in line with what OSHA would expect. I mean, ultimately, you know, knowing what that total volume of air that you've sampled is the most important fact that you need.
Okay. Here's a question from Kevin. Is the internal calibration system considered a primary calibration source?
I would say it is, well, that's kind of a tricky question, because if you could remove it from the pump, it would be a primary source. But it's not removed, can't be removed from the pump. So I would not, it would be kind of it may be a gray area. I'd have to check to see what the specification or how the determination would be to say whether it was primary or as a secondary source.
Okay. There's several questions from Jennifer, and she says her first question is, can you set up the data logging for flow rate at specific intervals?
Currently, no. We do not have a feature that allows that. But again, you know, as I said, this is, you know, hopefully as a learning experience for everyone, and something that, you know, if people have suggestions or things that they would like to incorporate or see, we're more than, you know, more than welcome to send those requests or concerns, and we'd like, you know, try to, you know, definitely incorporate to see if that could be a feature in the pump. Sure.
Okay. What is the expectation if there is an episode of the flow rate being above 10% of the initial flow rate during the sampling period? Would it be discarded even if the flow rate goes back to the proper flow rate?
Well, and that's one of the kind of the beauties of having an incorporated calibration device into the pump. What that does, if you remember, it continually measures the flow rate. So whether or not your flow rate changes, goes beyond a certain value, I mean, that's going to be up to the person who's actually the sampler themselves, what they want to do with the data, but at least you have an idea of what that, and have a true value of that flow rate. Now, pumps have, in general, have basically what they call a constant flow feature, which tries to maintain, a pump tries to maintain a specified flow rate within a certain range. Now, if it goes out of range, what happens is that some pumps will fault. You'll get faults. They'll either shut down and restart and go through this whole process. But I mean, that's only because you have no idea of what occurred or how long or what that event and your flow rate truly look like. But if you're recording and you have a record of what your flow rate is over that whole sampling period, you know that volume of air that you've sampled, regardless of where your flow rate goes. So, for instance, in most cases, your pre and post flow rates don't match up. Well, what happened to my flow rate? You know, was there, you know, particulate matter in the air that, you know, basically kind of plugged up my sampling media a little bit and caused an increase in back pressure, so my flow rates are now a little off. If that occurs, you know, how does that occur? Is that a linear occurrence, or did all of a sudden something was introduced at a specific moment and now your flow rate has changed? Well, recording over that whole sampling period, you can see exactly where that happened. You can see how much of it happened, so you can actually know what that true volume of air that you sampled, and not say, oh, well, I'm just kind of hoping that my flow rate is within a certain percent, and it hasn't changed. So if you have a flow rate that deviated in the middle and was the same at the beginning and the end, but you have no idea what happened to it in the middle, so what do you do then? At least this gives you some confidence that nothing happened, or you can see that something did happen.
Charles asks, is high flow and low flow in the same package?
High flow, flow range for the pump, I mean, and everybody has pumps that are designed, and they're all different as far as flow rates go. There are certain ranges where people cover, and the reason why you see so many different pumps, even between manufacturers, whether it's some features or not, some have high flow, medium flow, low flow, it's because not one pump can cover the full range. Our pump, obviously, we can look at low flow, we can look at medium flows, but we certainly can't go very high flow. Since it's a dual kind of pump design, what we've incorporated is that you can actually take two ports, the two independent sampling pumps. Basically, this is two pumps put together. You can use both of them together in conjunction. So maximum flow rate per channel, say, would be you can do 2.5, maybe 3 liters a minute per channel. So you can do up to a maximum of, say, maybe 5 to 6 liters per minute in that kind of situation. So we can go, so we try to cover as much range as possible without sacrificing too much. I mean, as you get towards the ends, obviously pumps, kind of have a sweet spot where they work. So that's, our low end, we're looking at 50 mils per minute easily. I've done work and I've set up sampling at 30 mils per minute. 20 mils per minute gets a little tricky, but certainly, hopefully there aren't too many people looking at that kind of a low flow situation.
Okay. Here's a question from William. Do the quick disconnect tube connectors have at least the same resistance as hose to pump, so they're not inadvertently pulled loose by personnel?
Yes, they actually have. It's a locking mechanism. So the way they operate is it's almost like a spring-loaded collar, metal collar that actually comes in and kind of goes into a recessed or indented channel in the connection. So it does make a positive connection and has a locking device. And it's easily removed by pressing a release tab.
Okay. A question from Philippe. Can this pump calibrator assembly be used to calibrate a second pump?
No. No, because what would needed to, in order to do that, you would actually have to. It's the pump is calibrated based on its flow, the way air flows through it. So if you're going to try to calibrate, use it as a calibrator for another pump, you would have to actually have a calibration for that whole system and not just the front part of the system, if that makes any sense.
Okay. Question from Doug. Does the calibration device have any control over the pump flow rate?
Yes, it does, and that's how kind of like the beauty of this whole thing. Wait a minute. Let me get back to. Oops, I'm on the wrong screen now. Kind of the beauty of what's going on with this is that when you set the pump for a specified flow rate, what it's doing is it's telling the pump to start to achieve that flow rate. Now, the pump's going to say, okay, well, I'm going to get to whatever flow rate you set me at, and the calibration part of the pump is going to say, well, you're not at that flow rate, or you are at that flow rate. I'm going to tell you to actually speed up or slow down to stay at whatever flow rate you have me set at. So what that does is when you hook it to your sampling train, now sampling trains are all going to have various back pressure numbers depending on what you're hooking to, whether it's a cassette or a Orbo tube or some other type of media, a cyclone sampler or anything like that. They're all going to have very different back pressures. So those back pressures are going to kind of have an influence on that sampling pump as far as trying to maintain flow rate. So what this does is that calibration device sees what flow rate is coming through your sampling media and into the pump. And it says, well, you are not operating at what you set me at. So I'm going to change how you actually, what kind of flow rate, or, I'm going to speed you up or slow you down and adjust you to get me that flow rate.
Okay. A question from Boris. What kind of microcontroller do you use, and could it be reprogrammed by the user?
Well, it's a mass flow sensor. It's all electronic. The computer part, when you that you have the ability to download log files after you sample, that you have no access, or consumers don't have any access into what we call would be a developer portion of that programming. So there's no way to change any of the electronic settings in the pump. So once the pump is calibrated, it stays at that point until you have it recalibrated. What makes the calibration of the pump a little bit more interesting is that the pump calibration, it's done over multiple points. So it's not just a few points or a handful of points. It's over the pump's flow rate range, and then that kind of that data file or that calibration file is then downloaded into the pump by the manufacturer or whoever is going to be doing the recertification, downloaded into the pump, and it gets uploaded in that fashion. So the customer really never sees or has control over changing any of the calibration in the pump itself.
Okay. Another question from Boris. What is the minimum maximum flow range?
Minimum flow rate range, I'd say I'm doing 30 mils a minute easily. If you need to go lower, you can play a few little games. You can actually sample lower, but what the pump does, it moves into what we call a pulsed mode. So it actually, the piston or the pumping mechanism turns or moves in a kind of a pulsed movement in order to achieve that low flow, just because of the kind of like the physical restraints on the pump, chamber sizes and things like that. So what you can do in essence to get around some of that feature, pulse mode, is if you really want to go really low, if you put enough back pressure restriction on it, once there's enough back pressure restriction on the pump itself, the pump will actually go into a continuous mode in order to achieve that flow rate. So maximum flow rate, we're looking at, I'd say comfortably, 2.5 liters a minute. In a combined mode, you can run, 5 liters a minute.
Okay. Stephen has a follow-up to an earlier question about whether the integrated calibration device would be considered a primary calibration device. And he asks, what is the principle of the operation for the integrated calibration device? For example, does it operate as a thermal wire device that measures the cooling of sampled air as the air flows across the wire? or does it operate like a rotameter, which balances forces?
Well, it's what the calibration device is. It's actually a mass flow sensor. So it would operate like almost like a hot wire, but it's actually not a wire. It is actually a sensor platform. But it does operate off of a heat mass transfer.
Okay. Belinda asks, do you see this becoming a direct read air sampling pump?
Well, now direct read, I mean, right now, I mean, it will tell you what the volume of air that you actually sampled. So currently, I mean, if that's what you're asking, it will tell you what that total volume is. There's no calculation on your part that's involved. It give you information, you know, typical information like, you know, what the barometric pressure, I mean, you know, temperature. I mean, even, you know, we even have a feature in there that you can look at humidity of your air sample, or the air that's coming in through the sampling. So, maybe not a true value, but it's wherever the pump is located. So, I mean, there is going to be a little bit of play in that number. But direct read, I mean, if you have a way to incorporate I mean, you could certainly pull an air sample through something that would give you an instantaneous reading, sure. It would give you air volume. This would basically provide you what that air volume that you sampled. So regardless of, you know, you can maybe whatever type of sampling media you want to hook it to, it could work in conjunction with that, sure.
Okay. The next question, is the device able to send a warning message once the flow rate is dropping or below a certain threshold?
It does have a warning. I mean, there are faults set up on the pump, so it will record and tell you that there were faults that occurred. Faults basically are going to be a percentage of the flow rate that you have set it at. Now, even though you have a fault or a pump flow rate moves outside of it, you know, a specified window of a flow rate, that for most cases, I mean, I'm not sure what people do with samples that actually have that situation occur, but if you have a record of what the flow rate was at those points and can see it up until that point, and even if the pump still maintains or still runs, and see what the flow rate is currently and continually, flow faults are you know, not things to be truly worried about, because you're actually measuring or know that total volume of air.
Okay. And Jennifer asks, have you done side-by-side sampling to compare this pump with a quote-unquote historic pump, and was there a significance in the volume collected?
I haven't. Those are some actually some experiments that are going on right now. We are looking at other. I mean, we're not looking at, or we don't want to really do a lot of comparative work with other pumps out on the market, only because what we're trying to do is trying to get, or a lot of the testing we would have on the slate would be to look at how it and how accurately it will give you the number that you're looking for. I mean, you know, regardless of, and hopefully other pump manufacturers, you know, see what we've done, and you know, maybe they like to do something along the same lines, and you know, just really, you know, help what the IH are doing out in the market, you know, in their work, and getting a real number, or as best a number as can be available given technology today.
Okay. Cheryl asks about the recharging time. What is the recharging time?
If you plug it into a wall charge, we're looking at 4 to 6 hours. You charge USB. There's been some kind of discussion about how fast the USB charge would occur. With USB, if you think about a USB, it has the capability for either doing a 1 to, depending on the configuration, 1 to 2 amps. But with that 1 to 2 amps, I mean, the wall charger that we have, it puts, I think the current is about 2 amps, so I would say it's probably going to be about the same. So depending on actually the capacity of the battery that you USB charge it with, that it would make a difference. Now, if you plug it in USB to, say you want to look at the data and you plug it into your laptop, connect it to your laptop through a USB, that charging obviously I think would be a little bit lower, since that's half volt 1 amp or 2 amps. So that charging will probably be a little bit longer. But one good thing is that you're always sending current to the pump at that point. So as you're actually looking at it plugged into your laptop, you're actually charging it, or trying to charge it, and or maintain a battery charge to it.
Okay. Will you be able to read the pump flow rate in real time?
In real time? Well, in real time, I would say absolutely you cannot do that, just because how fast the sampling time rate is for that mass flow sensor. But in real time, I mean, if you want to look at how your pump, what the flow rate is doing, you can monitor and see what it's doing if real time is, say, a second.
Okay. And Belinda asks, are the pumps intrinsically safe?
We are, when the pump launches, we are actually in the final process of having the pump available in EX, and it will be, and that's how, I mean, the version that's going to be available will be an EX version when we launch it. So it will be intrinsically safe.
Okay. Gary, thank you so much. Thanks to all our listeners. We are just about at the top of the hour. I apologize to everyone whose questions I wasn't able to get to today, but you can see that our host has just chatted Gary's email address. I'm sure he'll be happy to respond to you if I wasn't able to get to your question today. Just a reminder that we have some other Synergist webinars coming up on the horizon. So keep your eyes out for notices about those events. And I'd like to thank Gary for his presentation, and Millipore Sigma for sponsoring today's event, and to all our listeners today.